Hello there, my name is Aial Ortoyukov and I'm an 11th grade student of Northeastern Federal University, SJSA.RU. The title of my project, The Effect of Electrostatic Field on EM Images and the Analysis of Images. Scanning electron microscope is a type of electron microscope which is used for obtaining high-resolution images of biological and non-biological specimens. Obtained images are formed by scanning the specimen surface with a focused beam of electrons. The image quality can be affected by E fields that are charged by irradiation. Earlier specimen surfaces were coated with conductive materials, which is unsuitable. Nowadays, due to the use of low voltages, approximately 1 kV, it's possible to research without coating. But the charge problem is still on, even with the electric. This paper targets to compare images quality with different conductivity, like conductor, semiconductor, and dielectric. Under the fact of the fall of electrons, their acceleration and hence the fall will be carried out using the potential difference on the electron gun. And electrons hitting the surface of the substrate, simplified to a simple disk, will form an electric field. The force of the electric field acting on an electron from the side of the charged disk is F. On the other hand, the electron being accelerated by the field between the anode and cathode acquires kinetic energy that we see in first formula. An electron is decelerated, according to Newton's second law that we see in second formula. We suppose that at 50,000 magnification the square of the scanning window equals 1 square micrometer. We assume that the decelerating field of the disk appears from a distance approximately 10 micrometers. From formula L, we find acceleration in third formula. Substituting into second formula and taking into account first and third, we find the electric field of the disk in fourth formula. The E field strength created by the charged disk is E, where sigma is surface charge density of the disk. In fifth formula we find this sigma. In sixth formula we find the charge on the square of scanning window. In seventh formula we find the quantity of electrons that needed for this E field. The value of the electron beam current equal to 40 micrometers. Then from the definition of the current we will find the time to create this E field in eighth formula. To compare, we took substrates made of glass, aluminum and silicon. Table 1 showed that observed round bodies in the image are erythrocytes on glass, aluminum and silicon substrates. In addition, objects with size from about 10-15 to 113 nanometers are visible on the silicon substrate, which are not visible on glass and aluminum substrates. The absence of observed nano-sized objects on the glass surface can be explained by the limitation of charge drainage on the substrate due to its dielectric properties. When using aluminum substrates, a possible cause of smearing is the appearance of a repulsive electric field at the metal object interface, which prevents the charge from draining from the surface. Conclusion: SEM examination of blood smears showed that when we using silicon substrates, nanometer-sized objects were observed that weren't observed on other substrates. It's possible that this is due to the outflow of the charge from the surface from the object under study, accumulated during the irradiation with an electron beam, which make it possible to obtain images of nanometer objects. To simplify the calculations, it's assumed that the incident electrons are distributed over the surface and do not penetrate deep into the material. In this case, the electric field will be equal to the field created by the charged disk. It was found that at voltage between the anode and the cathode of the scanning electron microscope, approximately 1 kV, 11,000 electrons are sufficient to charge the scanning field with an area 1 square micrometer. The charging time is only 0.04 nanoseconds. The experimental results carried out confirm that nano-sized objects are not observed on the insulating material, which are clearly visible on the conducting material.